Hello everybody and welcome to Bash Course Quarantine Physics 2. My name is Faith and today we're going to talk about magnetism. Okay, so magnetism is the property of attracting metal. The ends of magnets are called its poles and they're designated as north and south. These poles are going to be repulsive if they're alike and attractive if they're opposite. However, poles cannot be alone, they're always paired. Magnetic field lines are going to go from north poles to south poles, and they're going to continue inside the magnet as well. Since there are no unipoles, all magnetic field lines are going to form closed loops. Side note, the north pole of the Earth is actually a south magnetic pole, and the magnetic poles of the Earth are slightly offset from its rotational axis. Moving on, electric currents can generate magnetic fields. These will appear as circles around a wire, and they're going to surround it in the direction dictated by the right-hand rule. Okay, so let's say that this loop represents your coil of wire, and it's got a current flowing through it. So to use the right-hand rule, you take your right hand and you put your thumb in the direction of current. So let's say current's flowing this way. Then you wrap your fingers around the loop, and the direction that your fingers curl around the loop tells you the direction of the magnetic field. So in this case, it's curling around the wire this way. If current is flowing the other way, you just put your thumb in the other direction and wrap your fingers around the wire that way to show you which way the magnetic field circles turn. A magnetic field will exert a force on the wire as demonstrated by F equals ILB sine theta, where B is going to be our magnetic field. The direction of the magnetic force is also determined by the right-hand rule. Okay, so now we're going to talk about the right-hand rule for a current-carrying wire that is exposed to a magnetic field and the direction of the magnetic force on that. So if you have a wire like this, and it has a current, let's say the current's going this way. Point your fingers in the direction of the current. Then, if there's a magnetic field that it is exposed to, you want to curl your fingers in the direction of the magnetic field. So let's say the magnetic field is coming towards you. You curl your fingers in that direction, and the direction that your thumb is now pointing is the direction of the magnetic force. So if the current's going this way, but the magnetic field is going away from us, we have to turn our hand like this to be able to curl our fingers towards the magnetic field. And now the magnetic force is down. But wait, that's not the last right-hand rule, there's another. For charges moving in a magnetic field, the magnetic force is given by F equals QVB sine theta. If you have a charge that is moving in a magnetic field, and you want to find the direction of the magnetic force on that charge, you're going to use this right-hand rule. So your thumb is going to be the velocity. Your index finger is going to be the field, and your middle finger is going to be the force. So if your velocity is going to the left, and your field is going into the page, then the force is going to be down. Just like that. This tells us that if the particle moves parallel to B, the force will be 0, and if the particle moves perpendicular to B, the force will be maximized. Often you will see this magnetic force act as a centripetal force on particles. The magnetic field caused by a long straight wire relates directly to the current and inversely to the radius from the wire. This equation is B equals mu naught I over 2 pi r, where mu naught is the permeability of free space, 4 pi times 10 to the negative 7 Tesla meters per amp. Okay, so let's say we have two current-carrying wires, wire 1 and wire 2. Wire 1 has a current of I1, wire 2 has a current of I2. They are separated by a distance d, and wire 1 has a length of L1 while wire 2 has a length of L2. So if we want to find the force on wire 2, then we're going to have to take the magnetic field from wire 1 at wire 2. According to the equation we just learned, the magnetic field is mu naught I over 2 pi r. Here, the current causing the magnetic field is I1, so you have mu naught I1 over 2 pi, and the distance is d. So that's the magnetic field at wire 2. So, according to the earlier equation, the force on wire 2 is going to be equal to ILB, assuming everything's perpendicular, which it is here. So, F is equal to I, the current on wire 2, I2, times L2, the length of wire 2, times B, which was mu naught I1 over 2 pi d. So if you want to find the force per unit length, you're going to take this and divide by L2. And you're going to get be mu naught I1 I2 over 2 pi d. If you have a wire coiled many times, it forms something called a solenoid, and its magnetic fields are additive based on the fields of each coil. One end of the solenoid is the North Pole, and the other end is the South Pole. The equation for the magnetic field inside a solenoid is B equals mu naught N I over L, the length of the coil. An iron core solenoid is called an electromagnet. So we've talked about how current can create a magnetic field, but can a magnetic field induce an EMF? The answer is yes, it's called electromagnetic induction. However, this only occurs when magnetic field is changing, otherwise no induced current is produced. If the magnetic field changes more quickly, more current is going to be induced. But the EMF that is produced also is going to depend on the area and the angle of the loop of wire to the magnetic field, which is defined as the magnetic flux through the loop. This whole relationship is expressed as Faraday's law, where epsilon equals negative delta phi, which represents electric flux, over delta t. This can be multiplied by however many loops there are. Flux, or phi, is equal to BA cosine theta for a constant magnetic field, which demonstrates that if the area vector is perpendicular to the magnetic field vectors, there will be no flux at all, since flux is going to measure the amount of magnetic field that passes through a region. The negative sign in Faraday's law actually relates to another law called Lenz's law, which states that the induced current will act so that its magnetic field will oppose the initial change in flux. Let's look at a quick example. All right, we're going to be taking a look at Lenz's law. If we have this coil, as we pass the bar magnet from beneath the coil of wire up through it, you're going to be increasing the upward flux through this loop of wire. So the induced current is going to act in a direction such that the magnetic field it produces opposes that change in flux. So it's going to want to create downward flux, which, according to the right-hand rule, means that current must be flowing this direction, clockwise, to create more downward flux. However, as it leaves the loop of wire, the loop is going to want to resist that change in flux. This means that it's going to induce a counterclockwise current so that it has upward flux through the loop of wire. There's one more type of problem which involves an induced EMF due to a moving conductor, often with a bar moving to change the area of a circuit. EMF will occur and can be shown to be given by the equation epsilon equals BLV. Okay, so there's your really quick overview of magnetism. If you want a more in-depth dive into any of these topics, make sure to let us know, and we'll try to make that happen for you. Thank you for watching Bash Course Quarantine Physics 2, and we'll see you next time. The Bash Course Quarantine team is Sandro Ansari, Sam Mencimer, Eamon, Pasha, Ishaq, Sarah Orozco, and myself. Please put any questions you have in the comments below, and we'll try to answer them or find someone who can. Thank you for watching Bash Course, and as they say in my hometown, oh my EOSH.